So pressure of gases has a big impact on our weather. Wind is caused by variations in pressure. I mean, you stop and think about it. What makes wind? Why does the air start moving? Right? It's not like when you fan yourself and you're using an object to move the air. There's nothing out there making the wind happen. Yeah, sometimes we get these big gusty winds, and other times it's really still. And it all has to do with pressure differences. And that's what meteorologists are looking at when they try to predict what's going to happen next with the weather. You'll sometimes see a map something like this, where they have a high pressure region and a low pressure region. So high pressure is usually associated with clear weather, nice weather. Low pressure is generally associated with unstable weather. We also see variations in atmospheric pressure as you go farther away from the center of the Earth, so increasing altitude. So if you've ever driven up the mountains into like Grant Grove, you know that the air pressure up there is less. So if you're to run around up there, you're going to get out of breath more easily because the air is literally thinner. It's less concentrated. And so the same amount of breathing doesn't get you enough oxygen, and so you have to breathe harder to get the same amount of oxygen. So the pressure decreases with increasing altitude, and that pressure is dependent on the number of gas particles in a given volume, or the concentration of the gas. So here we have two, these look like mason jars with gases in them. So the mason jars are the same size. This container has fewer particles and that has more particles. The pressure here is caused by the force of these little particles hitting the sides of the container. And so when there are fewer particles in this volume, there's going to be fewer collisions, and so lower pressure. Higher concentration, more particles in a given volume is going to be higher pressure. Does that make sense? So this is also related to going up into the mountains. As you go up the hill, you get this popping sensation in your ears, right? This happens when you're flying an airplane as well. We say our ears pop because that's what it sounds like, but actually your eardrum isn't rupturing or anything like that. So here's a diagram of your ear. So you've got your outer ear and your middle ear and then the inner ear. And between your middle and inner ear is the eardrum. And the eardrum is waterproof and airproof, and it vibrates, and that's what your body picks up those vibrations, and you interpret that as sound. Well, there's some air present in the inside of your eardrum, inside. And so that's connected through a eustachian tube down into the back of your throat. So what happens is, as you go higher up in altitude, the pressure outside decreases. The atmospheric pressure is less as you go higher and higher. But the inside pressure remains the same as what it was where you started. And at some point, that pressure difference begins to become a little uncomfortable because it causes your eardrum to bulge. The pressure pushes the eardrum out. Now, normally that's just sort of a sensation of pressure. If you have an ear infection, though, that can be exquisitely painful, just really, really painful. What happens when your ear pops is that the pressure in the inner ear escapes through your eustachian tube, and we detect that sensation as a popping sound. The reverse happens when you come back down, and then you have low pressure on the inside and high pressure on the outside, and your eardrum bulges the other way. And then again, you have to get your ears to pop to equalize that pressure. Any questions about ears? That's why babies scream on airplanes. Their eustachian tubes are smaller and it's harder for their ears to pop. So they're crying because their ears hurt. That helps you be more sympathetic towards them. How do we measure pressure? Here we have an illustration of a Mercury Barometer. Now, there are much fancier versions, but this is the original type of barometer, and even though we don't use these anymore, it's convenient to talk about because it's easy to understand what's going on here. So you can make this barometer by taking a long glass tube and filling it with liquid mercury and then inverting it into a dish of liquid mercury. Now, if you were doing this with water, you may have played around with inverted cups in the bathtub or the sink when you were a kid. You know, you can lift the cup up, and as long as the opening of the cup is underwater, the water will stay in the cup, right? None of it will run out. If we do this with mercury and the tube is long enough, mercury is much more dense than water, and so some of the mercury will come out. And what's left up here is a vacuum. So why doesn't all of it run out? Well, what's keeping this from all running out is atmospheric pressure pushing down on the surface of the mercury out here. For this mercury to escape, this mercury has to go up. And atmospheric pressure is pushing down on it. The mercury in the tube here is trying to go down because gravity is pulling on it. And so we have this balance between gravity pulling down on the mercury and atmospheric pressure pushing here, which causes the mercury to stay up in the tube. So the exterior pressure can be measured with a ruler. You can measure the height of the column of mercury, and at sea level that's about 30 inches, 29.92 inches or 760 millimeters. And that's where this kind of strange unit, millimeters of mercury, came from. Like, how can you measure pressure as a length of an element? That's crazy. Well, it's how high is the column of mercury in that glass tube. So, millimeter of mercury, mmHg, is the pressure unit. So the higher the external pressure, the higher the column of mercury. The lower the external pressure, the lower the column of mercury. So millimeter of mercury is easy to understand in terms of the mercury barometer, but it's just kind of a strange unit. So it's also been given the name torr in honor of Torricelli, who first developed this type of barometer. So like cubic centimeter and milliliter, these are two units that mean exactly the same thing. Torr is a more modern name for a millimeter of mercury. I think it was intended to replace it, but we still use both of them, so we ended up making it more confusing. There are lots of other units for pressure, and the unit that you use depends on what you're doing with it and what sorts of pressure you're measuring. So the SI unit is a Pascal, which is defined as a Newton per square meter. Yeah? We are not going to use all of these. No, we're just going to use a couple of them. So the Pascal is the SI unit, and that might show up in like a conversion factor problem or something, but we'll rarely use that in chemistry. Pounds per square inch is what's typically used like for measuring the pressure in your bike tire or your car tire. It literally means pounds per square inch. Pound is a unit of force. Square inch is a unit of area. So there's that. And over here what we have are the values in these different units of air pressure at sea level. So we can see the size of the units here are very different. 14.7 psi is atmospheric pressure. That's 101,325 pascals. So the pascal is a very small unit. Here we have the torr, same as the millimeter of mercury, and average air pressure at sea level is defined as 760 torr, or 760 millimeters of mercury, and that's considered an exact number. We can also measure the height of the column of mercury in inches, and this is what the weatherman uses, 29.92 inches of mercury. And you can do that conversion. 760 millimeters is the same as 29.92 inches. It's just a length conversion. And then we also call this an atmosphere because it's 1 atmosphere of pressure at sea level. It's abbreviated ATM, no money involved there. And so one atmosphere. So the way the pressure units are given to us, all of these values are equal to each other. They are all the pressure at sea level. And so to do a conversion between pressure units is always one step. You don't have to go through a bunch of different things. You've got the unit you're given, the unit you want, and you just pick the 2 values out of here. Because 14.7 psi is the same as 29.92 inches of mercury. 1 atmosphere is equal to 101,325 pascals. Okay, so it's always just one step. So let's do an example. Your local weather report announces that the barometric pressure is 30.44 inches of mercury. Convert this pressure to psi, pounds per square inch. I recommend memorizing this top line, that an atmosphere is 760 torr, which is the same as 760 millimeters of mercury. That one we're going to use a lot, okay? I recommend memorizing that. This bottom one, well, actually, both of these lines I'll give to you on an exam so that you can just do the math and not have to worry about remembering funny numbers. And this is the way I'll give you pressure conversion units. So all of these things are equal to each other. So here if I have inches of mercury and I want psi, here's psi, here's inches of mercury, there's my relationship. I can do this in one step. So I've been given inches of mercury, and I'm going to go to psi, and I can do it in one step. So 30.44 inches of mercury times in a line, psi here, inches of mercury down there. And then I just go to this list here and I pull out the numbers, 14.7 for psi and 29.92 for inches of mercury. So this is 15.446 psi, which would round to 15.4 psi. The 760 is exact. The other numbers are not exact. So 14.7 is 3 significant figures, and that's why my answer has 3 sig figs. Any questions? Mm-hmm.
Where's the 14.7 from?
The 14.7 came from right here.
I don't understand why 14.7 is psi.
Well, because this table here tells me that 14.7 pounds per square inch is equal to 29.92 inches of mercury.
And I was saying like PA equals 14.7.
PA is pascals. It's a different unit. So instead of having a bunch of different relationships, like 1 cup is 8 ounces and 1 pint is 2 cups and 1 quart is 2 pints, instead of a bunch of different things like that, these are expressed as what's equal to 1 atmosphere. So 760 torr is 1 atmosphere. 760 millimeters of mercury is 1 atmosphere. 14.7 psi is 1 atmosphere. Did I do it wrong? I did. I typed in 31.44. It's Monday, right? Thank you. And thanks for calling me out on that because it's important. Yes, 14.955. So let's fix that. .955 psi, and so then that's going to round up to 15.0 psi. Any other questions? Yeah.
PSI to inches mercury isn't as exact.
Not exact, no. No. I started putting the answers up here because I do make these mistakes, and sometimes students just are like, oh, well, she must be right, I'm not going to say anything. And then I just end up telling the whole world, my YouTube videos go out there, and then people from the other side of the world say, how did you get that? And then, it's embarrassing, so I don't like that. So barometer is used to measure atmospheric pressure. Manometer, so meter means measuring something. Barometer measures the barometric pressure. A manometer measures a man, I don't know, or maybe a hand, a manometer, I don't know. Not sure exactly what that refers to. Manometer is used to measure the pressure inside of a container. And of course there are much fancier versions, but the simplest one involves a tube with mercury in it, not unlike the Mercury Barometer. So here we have a container that in this case has gas that's under pressure, and the manometer is attached to this. It's a U-shaped tube that's got liquid mercury in it. If this tube was open to the atmosphere on both sides, the levels of mercury would be equal, because nothing is, all we've got going on is gravity pulling down, and the atmospheric pressure pushing down is the same on both sides, and so they'll be equal. You can try that with a piece of tubing and put some water in there. And it doesn't matter what you do to the ends, the levels of the water are going to be the same. But here this end is not open to the atmosphere. It's connected to this high pressure gas. So this gas is putting pressure on this side. It's pushing down. You can imagine blowing down on this side of the hose, and that's going to cause the liquid on this side to go down, which forces the liquid on the other side to go up. Yeah, it's like pushing air through a straw. On this side, we have atmospheric pressure pushing down. And so what we see is there's a difference in these levels that can be measured again with a ruler, just like with the barometer. And that's the difference in pressure.
Would there be questions where it asks, it'll say like it's pushing pressure from either side, or something like that?
Well, you could have the pressure in the container be less than atmospheric pressure. And so then atmospheric pressure would be pushing down more, and this side would be up. And so there definitely could be and will be problems where it asks you to figure out the pressure.
So then would the pressure still be the same between the difference between the two?
The difference in pressure between inside and outside is equal to the height difference of the columns. So if atmospheric pressure here is 760 millimeters of mercury, and this distance is, say, 10, let me write that down because I'll forget what I just called it. Let's say this is 10 millimeters of mercury. If the pressure outside is 760 millimeters of mercury, that means that the pressure in here is this much more than that, right? So that means inside, this pressure is 760 plus 10, 770 millimeters of mercury. So you just add the difference to the one that's smaller. Any questions?